Hello everyone, myself Dr. Sriparna Saha, and in this artificial intelligence lecture series so far we have talked about knowledge and reasoning. Today we will be moving to our next lecture, that is the predicate logic. How to use predicate logic to represent knowledge. That is all about today's lecture. So let's start today's lecture. So this type of logic is also known as first order logic, or it can be in the short form known as FOL. In this particular logic, there are basically four components of this logic are. First component are the objects. That is, these are the things with individual identities. Like the examples, students, lectures, companies, cars. These are the some examples. Next, the properties. So properties of objects are those by which one particular object can be distinguished from the other. Like the color or the shape, that is the suppose blue, oval, even, large. That is the color or the shape of certain objects by which we can segregate one object from the other. Next is the relations. So relations that hold among sets of objects. Like one example is that Ram is the brother of Shyam. So then brother of is the relation. By that two objects Ram and Shyam are hold, or we can find the relation between the two objects. That particular component of the logic is known as relations. Another examples can be bigger than, outside, part of, has color, occurs after, owns, visits, precedes. These are the other examples of relations. Next, the functions. Functions are a subset of relations where there is only one value for any given input. So, functions are type of relations. But what's the difference, or what are the extra thing functions have? That there is only one value for any given input. Suppose I told you Ram is the best friend of Shyam. And this best friend, this best is a superlative thing. Superlative thing means only one can be the best friend of the other. So that is, as there is answer will be only one input. So then only one value can be obtained. Then those are the functions. Other can be further off, second half, more than one. These are the other relations as well as these are known as functions. So functions are the type of relations. These are the basics of FOL. Now in this logic, what are the things that need to be provided by the user? That is the constant symbols which represent individuals in the world. Function symbols which map individuals to individuals, like the father of, color of, these are the things. Then the predicate symbols which map individuals to truth values, that is greater, green, color, these are the things. Now, what the FOL is going to provide? That is the variable symbols, that is variables like A, FO, FOO, FY, XY, these are the different variable symbols. Then connectives. So connective is that is same as in predicate logic. That is not function, and, or, implies, if and only if, that is a bidirectional arrow. These are the connectives. Again, that FOL provides quantifiers, that is the universal quantifier that is represented by this way, and the existential quantifier that is represented by the reverse of E. So these are the two quantifiers that the FOL provides. Now the sentences are built from terms and atoms. A term denoting a real world individual is a constant symbol, a variable symbol, or a n-place function of n terms. That is x and f of x1 up to xn are terms where each xi is a term. A term with no variables is a ground term. An atomic sentence which has value true or false is an n-place predicate of n terms. A complex sentence is formed with atomic sentences connected by the logical connectives, that is the not P, P and Q, P or Q. If P then Q, or P implies Q, or P bidirectional way, that is P if and only if Q. That is where P and Q are sentences. A quantified sentence adds quantifiers, that is universal quantifier and the existential quantifier. A well-formed formula or WFF is a sentence containing no free variables. That is, all variables are bound by universal or existential quantifiers. That is, for all x, p, x, y has x bound as a universally quantified variable, but y is free. So, as we have already told about the quantifiers. So, the universal quantifier, that is for all x, px, means that p holds for all values in x in the domain associated with that variable. For example, if I told you that is if all dolphins belong to the mammal category, if that was the sentence, so that is for all x, dolphin x, that is belongs to, that is implies mammal x. So if one x belongs to the dolphin category, so it is implied that x will be a mammal as well, and it is true for all the other x's. Now, another thing, if I told you for the existential quantification, that is for some x, p means that p holds for some value of x in the domain associated with that variable. For example, the sentence is that some mammals lay eggs. That is, there will be some mammals, not all mammals, who are going to lay eggs. So that is existential quantification of eggs, mammal eggs, handling of lays eggs. That is the x. So if x belongs to the mammal category, then x can need to also lays eggs. It's not true for all the x's belongs to the mammal category, but there is some x's for which it is that they are going to lay eggs. That is, permits one to make a statement about some object without naming it. So this quantification scope, that is switching the order of universal quantifiers, does not change the meaning. In this example, you can check that the x and y, the position of the for all x and for all y is changed here. So that is, switching of these are not going to change the meaning. Similarly, you can switch the order of existential quantifiers. That is, for some x, for some y, px. So that is, for some y, you can take it from above here, then for x. So it can be over here. Switching the order of universals and existentials does change meaning. Everyone likes someone. So that is, everyone suppose is represented by the x. So that is for all x. Someone suppose is going to be represented by the y. So for some y, that is not all, but for some, that is existential quantification, then likes x comma y. So that is the everyone likes someone. Another sentence is that someone is liked by everyone. So someone, that is not all, that is some. So that is existential quantification y is liked by everyone. So for all x, then likes x comma y. Now let us talk about the connections between all and exist. We can relate sentences involving universal and existential quantification using De Morgan's laws. So that is the way you can represent. That is, this is, if this is, then if and only if this is, then this also be true. So that is, here the not form is there. So it is for all x. So if you take the not here, then it will be for some x. Here the not is there for all. So if you just take it over here, it will be for some x, not p. Right? Not px. Then for all x, px. So it will be for some x, that is not some x, not px. And same over here is that for some x, so it will be not all x, not p. That is the connection with De Morgan's laws. Now the universal instantiation, that also known as universal elimination. That is, if all x, that is for all x, px is true, then pc is true where c is any constant in the domain of x. One example can be, that is, for all x, that is jiggy eats everything, that is for all x eats jiggy eggs. So it is that eats jiggy ice cream. So that is, if that is ice cream belong to the x domain, then jiggy is also going to eat the ice cream. The variable symbol can be replaced by any ground term, that is, any constant symbol or function symbol applied to ground terms only. Existential instantiation, also known as existential elimination. From for some x px, we need to infer ps. See, that is the example, that is for some x is jiggy x. So that means is jiggy stuff. Note that the variable is replaced by a brand new constant not occurring in this or any other sentence in the knowledge base. That is, the KB is the knowledge base. Also known as columnization, constant is a column constant. In other words, we don't want to accidentally draw other inferences about it by introducing the constant. Convenient to use this to reason about the unknown object rather than constantly manipulating the existential quantifier. Existential generalization, also known as existential introduction. That is, if PC is true, then for some x, px is inferred. Example, that is, if jiggy ice cream, that is jiggy is ice cream is true. So there will be some x jiggy that's going to eat x, that is jiggy comma x. That is jiggy eats ice cream but does not infer that jiggy is going to eat chowmein as well. So if jiggy eats ice cream, you cannot, from that you cannot infer that jiggy is going to eat the chowmein. But there will be some elements that belongs to the category where what elements jiggy is going to eat. So for some x, jiggy is x. All instances of the given constant symbol are replaced by the new variable symbol. Note that the variable symbol cannot already exist anywhere in the expression. Now, let us have some English sentences and we'll be translating those English to first order logic or FOL. Every gardener likes the sun. That is the first knowledge you have for the English sentence here. So every gardener. So for all x, gardener x, that is x belongs to the gardener category. So likes x comma sun. So if Ram is a gardener, that means Ram is also going to like the sun. Right? Now the next sentence. You can fool some of the people all of the time. So you have two objects over here. One is the people, another is the time. So some of the people, that is for some x, person x, all of the time, that is for all t, and time t. So what is the implication? That is can fool x comma t. Next is you can fool all of the people some of the time. This particular sentence will be represented by two ways. Both of the representation are equivalent with each other. So that is all of the people. So people x for all x. Then it's going to be the implies that some of the time. So time t. Then for some t. Some of the time. So for some t. And can fool x comma t. So that is the representation. Now if we change this bracket over here there is no bracket. So we are making another bracket in this part. So if we make this type of bracket, then this person part is not dependent on the time. Person and time are the two different objects who are not dependent on each other. So that is this term for some t that will be can be taken over here. So it will be come over here. It is here in the beginning, but if we make a bracket over here, you can take it over here. So this is the equivalent representation of a same English sentence. Another sentence is that all purple mushrooms are poisonous. So for all eggs, mushroom eggs and purple eggs, that is, eggs will need to be belong to the mushroom category as well as in the purple category. And what are the implications? That eggs will be poisonous. Next sentence is that no purple mushroom is poisonous. So that is, it is again going to be represented by two ways. That is no purple mushroom. So no purple mushroom means that is not some eggs, purple eggs, ending with mushroom eggs, ending with poisonous eggs. Right? That is no purple mushroom is poisonous. Now here for all eggs, mushroom eggs and with purple eggs, implication will be not poisonous eggs. Right? That is another way you can say it, that is all purple mushrooms are not poisonous. This is here. Another example is that there are exactly two purple mushrooms. So there will be two mushrooms, right? So two will be, one is represented by the X, another is represented by the Y. So for some X, for some Y, X belongs to the mushroom category and X belongs to the purple category, and Y belongs to the mushroom category and Y belongs to the purple category. That is mushroom eggs, purple eggs, and not, that is X and Y are the two different mushrooms. So there is a term called not X is equal to Y, ending with for all Z, mushroom Z and purple Z. That is another mushroom we are taking into consideration, that is the Z. Suppose another variable, that is the Z. So what will be the implication, or it implies that X is equal to Z or Y is equal to Z. So either Z will be equal to X or Z will be equal to Y, but there will be two distinct. Next is a very simple example. Clinton is not tall. So not tall Clinton. Very simple. Last one is X is above Y. That is IFF. That is if and only if. So here there is a if and only if. It will be represented by the bidirectional equivalency. That is if X is directly on top of Y, or there is a pile of one or more other objects directly on top of one another, starting with X and ending with Y. So how to represent this? That is for all X, for all Y, above X, Y. It's a bidirectional equivalency, meaning that is on X, Y, or there will be some Z, where on X, Z and above Y, Z, Y. That is the way to represent it in FOL logic. So this is all about the basics of predicate logic. I hope you like this particular lecture video. Thank you everyone for watching this, and happy studying.